Welcome to Revised Chemistry with Mr. B. In this video I'm going to go through the whole of C9 Organic Chemistry topic. That's if you're studying for AQA Combined Science, sometimes called Trilogy. If you're studying for separate science or you're with another exam board, then just check your revision guide to make sure there's no other extra little bits that you might need to know. In this topic of organic chemistry, we learn all about molecules that are based on carbon atoms, and many of those useful molecules with carbon in them come from crude oil. So the first thing we're going to look at is how crude oil is formed. Crude oil was formed from plankton that lived in the sea millions of years ago, and when that plankton died, it fell on the seabed, and rather than it rotting away completely, it got covered by sediment and mud, and that kept out the oxygen and stopped it completely decomposing. Over millions of years, heat from inside the earth and pressure from different layers piling up on top turned that plankton into crude oil. Whereas with coal, that started out as plants and trees that were taking in carbon dioxide as they were photosynthesizing millions of years ago, and when they died, they fell into swamps. Again, they got covered by sediment such as mud, and over millions of years, the action of heat and pressure turned those plants into coal. So although they're both fossil fuels, and there are some similarities, crude oil started out as plankton in the sea, whereas coal started out as plants and trees that lived around swamps. Crude oil is a mixture of hydrocarbon molecules, and hydrocarbon molecules are made from just hydrogen and carbon atoms joined together. So I've got some models of hydrocarbon molecules here, and the black spheres are to represent the carbon atoms and the white spheres are to represent the hydrogen atoms. So here, for example, we've got a 1 carbon methane molecule, whereas here we've got a molecule that's got 4 carbon atoms, so that would be butane. And crude oil is a mixture of different length hydrocarbon molecules, from 1 carbon atom long all the way up to 100 carbon atoms long. And now I'm going to show you how the properties of hydrocarbons change as the molecule length gets longer. The first thing to notice is as we go from short to long hydrocarbon molecules, they're getting darker in colour. I'm going to try and pour out some of the shortest hydrocarbons, and we can see it's very runny, so we say it's got a low viscosity. If we compare that to the longer hydrocarbons, we can see it's more like treacle, and therefore we say it's got a high viscosity, or it's very viscous. There's 2 reasons why hydrocarbons get more viscous as the molecules get longer. First reason is because as the molecules get longer, they're more likely to get tangled up with each other. And secondly, as the molecules get longer, the forces between the molecules get stronger. We get stronger intermolecular forces compared to when we've got shorter molecules. We also see a trend in the boiling points of hydrocarbons. The longer the hydrocarbon, the higher the boiling point. And it comes back to those intermolecular forces again. Because the longer hydrocarbons have got stronger intermolecular forces, that's going to take more energy to overcome those forces. Therefore, they have a higher boiling point the longer the molecule. Let's see what happens when I set fire to these 2 hydrocarbons. So we can see the short hydrocarbon burns with a much cleaner flame, whereas the longer hydrocarbon burns with a smoky flame. Here's a very long hydrocarbon, we can tell by the dark colour, and let's see what happens when I try and set fire to that. It actually won't ignite at all. The longer the hydrocarbon, the more difficult it is to ignite. It becomes less flammable. So to recap how the properties of hydrocarbons depend on the size of the hydrocarbon molecule, if we look at the shorter hydrocarbon molecule, they are lighter in colour compared to the darker, long hydrocarbon molecules. The shorter hydrocarbons are less viscous or runnier, whereas the long hydrocarbon molecules are more viscous and kind of treacly. The shorter hydrocarbons are more flammable, they set on fire much easier, and when they do burn, they burn with a clean flame, whereas the long hydrocarbons are less flammable and they burn with more of a smoky flame. And finally, short hydrocarbon molecules have lower boiling points and longer hydrocarbon molecules have higher boiling points. When crude oil has been drilled out of the ground, the first process it undergoes is fractional distillation. And this is how we turn it into useful products like petrol and diesel. Now, crude oil is a mixture of hydrocarbons of different lengths, anywhere from 1 carbon atom long up to 100 carbon atoms long. And fractional distillation is a process that separates those into different fractions of approximately same length molecules. So we can see with these 4 fractions, the first fraction has got very short hydrocarbon molecules, second fraction slightly longer, third one longer still, and the fourth fraction has got some very long hydrocarbon molecules. So this is what fractional distillation is all about, turning that mixture into fractions of similar sized hydrocarbon molecules. This is how we carry out fractional distillation in the lab. In this flask down here, I've got some crude oil and it's been heated by an electric heater. So we can see the oil is starting to boil now, and it will be the smallest hydrocarbon molecules that are boiling and turning into a gas. Those hydrocarbon molecules will pass up the fractionating column, and when they get to the cold condenser, which is being kept cold by water flowing around the outside of it, they will then turn back into a liquid. So in the first test tube, we'll be collecting a hydrocarbon with the shortest molecules. We then turn up the heater to increase the temperature. Then the next size up hydrocarbon molecules will start to evaporate. They will pass up the fractionating column, and once again, when they hit the cold condenser, they'll turn back into a liquid. So by progressively turning up the heat of the heater and increasing the temperature, longer and longer hydrocarbon molecules are going to evaporate and then condense in the condenser. So as we keep swapping over the test tubes, we're going to be collecting gradually longer and longer hydrocarbon molecules. The first test tube will collect the shortest hydrocarbon molecules, and the last test tube will collect the longest hydrocarbon molecules. We can see the first fraction now condensing and dripping into the test tube. I'm now going to pour the contents of the first test tube onto a watch glass, and I'm going to try and set light to it to see how flammable it is. If it is the small hydrocarbons, it should be very flammable and burn with a clean flame. And there we go, straight away it sets on fire and it's a fairly clean flame. We've seen how fractional distillation can be carried out on a small scale in the lab. We're now going to look at how it can be done on a large scale at the oil refinery. And the oil refinery is where the oil is taken to after it's been drilled out of the ground, so it can be turned into useful fractions like petrol and diesel. When the oil arrives at the refinery, it's passed into this very tall structure called a fractionating column. And the first thing that happens to the oil is it's heated up. And that means that there's a temperature gradient in the fractionating column. It's hotter at the bottom and cooler at the top. As the crude oil is heated, those hydrocarbon molecules turn into vapours. And those vapours pass up the fractionating column, and as they rise up the column, they get cooler. So at some point, they're going to turn back from a gas into a liquid. In other words, they're going to condense. And as they condense, they exit at different points of the fractionating column. The short hydrocarbons with low boiling points condense and exit near the top of the column. And the longer hydrocarbons with higher boiling points condense and exit near the bottom of the column. So in this way, we separate out the crude oil into different fractions of roughly the same size molecules. So we get some really useful products such as refinery gases like butane and propane that can be used on barbecues, petrol that we use in vehicles, kerosene that's aircraft fuel, diesel that can be used in cars, buses and trains, fuel oil that heavy ships might run on, and bitumen that can be used to repair the roads. Many of the hydrocarbons that we get from crude oil make good fuels. So now I'm going to use this equipment here to test what gases are given off when we burn a hydrocarbon. At this end I've got my hydrocarbon burning, which is just a candle, and over at this end, when I turn the tap on, the pump is going to pump any gases given off by the candle through these different tubes, and we're testing it with a variety of chemicals. So over here in this U-tube, we've got some blue cobalt chloride paper. Here in the middle, we've got some colourless lime water. And over here, I've got some universal indicator solution, which is starting out green. Let's see what happens when I turn the tap on. You'll notice that the different solutions start bubbling as it's drawing the gases given off by the candle through these different tubes. And we'll come back to that in a few minutes. So I'll turn off the pump now. We can see that the cobalt chloride paper has gone from blue to pink. That shows that the burning fuel is giving off water vapour. I've put some blue card behind the lime water so you can now see it's turned cloudy or milky. That shows that carbon dioxide is being produced. And the universal indicator has gone an orangey yellow, so that's slightly acidic, so some sort of acidic gases are also being given off. There's two types of combustion. The one I've showed you was complete combustion, where there's plenty of oxygen, so the fuel fully burns. And when you get that situation, the products are carbon dioxide and water. For example, if the fuel was methane, like we use at home on the gas cooker or in school using a Bunsen burner, the methane reacts with oxygen, it's an oxidation reaction, and it produces carbon dioxide and water. And we can see by looking at the symbol equation where those products come from, because methane is a typical hydrocarbon made from hydrogen and carbon atoms. So when the carbon part of the hydrocarbon reacts with oxygen, it makes carbon dioxide, and when the hydrogen part of the hydrocarbon reacts with oxygen, it makes the water vapour. The second type of combustion is incomplete combustion, and this is where there's not enough oxygen getting to the fuel. So it may be, for example, somebody's got a faulty gas fire. This time the fuel reacts with less oxygen to make carbon monoxide and water, and that's a problem because it's toxic, because it joins with the hemoglobin in your red blood cells, so your red blood cells can't carry as much oxygen as they should be carrying. Now, methane and oxygen under incomplete combustion conditions would make carbon monoxide and water, and this would be the equation for that reaction. Sometimes the fuel burns with even less oxygen, and instead of the carbon in the hydrocarbon making carbon monoxide, instead it remains as unburnt carbon, which you would see as soot building up. And this happens if you've ever heated up a beaker with a Bunsen burner with the air hole closed. So not enough oxygen is getting to the methane, and it forms black soot on the outside of the beaker. This model shows an alkane molecule. Alkanes are hydrocarbon molecules because they're only made out of hydrogen atoms and carbon atoms. And we can tell it's an alkane molecule because they're only joined together with single covalent bonds. So it's also known as a saturated molecule. When it comes to naming chemicals, we have a logical system so you can actually work out the name. Now, alkanes all belong to the same family of chemicals or homologous series, so they all end in -ane. The start of the alkane's name depends on how many carbon atoms are in that main backbone of the molecule. So you need to remember these prefixes to the name. So if it's got one carbon atom, it will begin with meth. So if it's an alkane, it will be called methane. 2 carbon atoms, eth. 3 carbon atoms, prop. 4 carbon atoms, bute. So an alkane with 4 carbon atoms would be called butane. And then it gets a little bit easier because some of these words you've come across in maths. For example, a pentagon has 5 sides, whereas an octagon has 8 sides. So if we had an alkane with 8 carbon atoms in the main backbone of the molecule, it would be called octane. So if we want to name this alkane molecule, it's got 1, 2, 3, 4 carbon atoms, so it would be called butane. This alkane has only 2 carbon atoms, so it would be called ethane. I'm now going to show you how to draw alkane molecules. So starting with propane as an example, the N part tells me that it's an alkane with single covalent bonds. The prop part tells me that there's 3 carbon atoms. So we'll start off with those 3 carbon atoms and join them together with a single covalent bond. Now what you need to remember is that every carbon atom is going to make 4 covalent bonds. So this one's making 1, so we'll give it 2, 3, 4. This one is making 1, 2, 3, 4. This one is making 1, 2, 3, 4. And it's a hydrocarbon molecule. We've already drawn the carbon atoms, so we need to draw the hydrogen atoms. And what we've drawn here is the displayed formula. Now we could also write down the molecular formula. The molecular formula is simply counting up how many carbon and hydrogen atoms there are in the molecule. So we've got 3 carbon atoms, making sure the 3 goes down there as a subscript, and we've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms. So that would be the molecular formula of propane. I'll show you another example. We've got pentane this time, so the pent tells me there's 5 carbon atoms. The last part of the name tells me it's an alkane with single covalent bonds. And then we're going to make sure that every one of those carbon atoms makes 4 covalent bonds. That's making 1, 2, 3, 4, 1, 2, 3, 4, and so on. And then we need to fill up with hydrogen atoms because an alkane is a hydrocarbon made from just hydrogen and carbon atoms. So that is the displayed formula of pentane, and if we wanted the molecular formula, we've got 5 carbon atoms, and if we count up all the hydrogen atoms, we've got 12 hydrogen atoms. I've just picked out some alkanes here and written their molecular formulas next to them, and we can see a pattern. And that pattern is, whatever the number of carbon atoms is, if we double that number and add 2, we get the number of hydrogen atoms. So double 3 is 6, add 2 is 8. Double 6 is 12, add 2 is 14. 8 times 2 is 16, add 2 is 18. So to get the number of hydrogen atoms, double the number of carbons and add 2. And the way we can write that is known as the general formula. And that is CnH2n plus 2. So whatever the number of carbon atoms is, we double it and add 2 for the number of hydrogen atoms. And that is the general formula for alkanes. This molecule belongs to a different family of chemicals or a different homologous series called alkenes. We can tell it's an alkene because it's still a hydrocarbon made of just hydrogen atoms and carbon atoms, but this time it's got a double covalent bond between 2 of its carbon atoms. And for that reason, we call it an unsaturated molecule. We still use the same system of naming these chemicals. This time they will all end in -ene because it's an alkene. So this substance has got 1, 2, 3, 4 carbon atoms in the main chain. So it will begin with bute and end in -ene. So we call this one butene. Here's another example of an alkene because it's got a double covalent bond between 2 of the carbon atoms. This time there's only 2 carbon atoms, so the name is going to begin with eth. So this substance is ethene. When drawing the displayed formula of an alkene, we follow the same rules that we had for alkanes. So bute tells us there's 4 carbon atoms in the main chain, so let's draw those 4 carbon atoms. The ene part of the name tells us it's an alkene, so that means we're going to have a double covalent bond between 2 of the carbon atoms. So do we place it here, here, or here? The answer is it doesn't matter, you can choose. So let's decide to put it there. And the other carbon atoms are joined by single covalent bonds. As before, each carbon atom must make 4 covalent bonds. So this one's making 1, 2, 3, 4. 1, 2, 3, 4. Now we need to be careful here. This one is already making 1, 2, 3. So we only need to draw one more covalent bond. Does it go here or here? The answer is it doesn't matter. So let's put it there. This one's making 2 covalent bonds. So let's give it 2 more. Now it's making 1, 2, 3, 4. It's a hydrocarbon. We've drawn the carbon atoms. So now we need to draw in the hydrogen atoms. And this will complete the displayed formula of butene. Now, if we want to also write the molecular formula, we count up the number of carbon atoms. There's 4. And if we look at how many hydrogen atoms there are, there's 8. So C4H8 will be the molecular formula. Let's do one more example. So this time I've chosen hexene. Hex tells us there's 6 carbon atoms. So let's draw those in first. And then we need to put the double bond somewhere. This time I'll put it here. The other carbon atoms, remember, are joined together with single covalent bonds. And then we need to make sure every carbon atom is making 4 bonds. This one's making 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, and so on. And we get to the end here, 1, 2, 3, 4. Then we need to put the hydrogen atoms in at the end of each of those bonds. So this would be the displayed formula of hexene, which is an alkene with that double bond. The molecular formula, if we count up the carbons, we've got 6. So C6, and there is 12 hydrogen atoms. So the molecular formula would be C6H12. This time, if we look at the pattern of the molecular formulas, propene C3H6, pentene is C5H10, octene is C8H16. So we can see that whatever the number of carbon atoms is, you simply double it to find out the number of hydrogen atoms. So that means the general formula for alkenes is CnH2n. If we're looking at the displayed formulas of an alkane and an alkene, it's easy to spot the alkene because it's got the double covalent bond. But when you've actually got the substance in a test tube, they look exactly the same. Here's an alkane, this is hexane, and that looks exactly the same as hexene, which is an alkene. So to tell the difference between the two, we use a substance called bromine water, which starts off an orangey brown colour. And if I first of all add a few drops to the alkane, we can see there that the bromine water stays orangey brown. We can see it in the bottom of the test tube still. If we do the same test with the alkene, add a few drops of bromine water to the alkene and give it a shake, then the bromine water loses its colour. We say it decolorizes bromine water, or it changes from orangey brown to colourless. Before moving on, we'll just recap on what we've learnt about alkanes and alkenes. So here we've got an alkane, this one is propane, and we can see it's only got single bonds, and that means it's a saturated molecule. Whereas the alkene has got that double bond between 2 of the carbon atoms, that means it's an unsaturated molecule. And when we test those with bromine water, the alkane would have no change on the bromine water. It would stay orangey brown. Whereas the alkene changes the bromine water from orangey brown to colourless. When we look at the general formulas for an alkane, it's CnH2n plus 2, whereas from an alkene, it's simply CnH2n. We've already seen how fractional distillation is used at the oil refinery to turn crude oil into useful products like these. And it does that by separating out the hydrocarbons according to their size. So the shorter hydrocarbons exit near the top of the column, whereas the longer hydrocarbons exit near the bottom of the column. The problem with that is that if that was all the oil companies did, they would quite easily sell the shorter hydrocarbons like petrol that are in high demand, and they would have lots of the longer hydrocarbons left over like bitumen, which is used for fixing roads. So the clever part is the oil companies turn the longer hydrocarbons, which we don't need much of, into shorter hydrocarbons like petrol that are in high demand. And it does that by using heat to break the long molecules into shorter hydrocarbons, and that process is called cracking. This equipment can be used to carry out cracking in the lab. In the test tube I've got some rock wool soaked in Vaseline, and that's the long hydrocarbon that I'm going to try and crack. Here I've got some broken tile in the test tube, and that's going to act as a catalyst to speed up the reaction. So the first thing we do is we get the catalyst nice and hot. So I would heat up the catalyst with a Bunsen burner, and then I would heat up the Vaseline, our long hydrocarbon, to turn it into a vapour. So that vapour then passes over the hot catalyst, and the heat makes the molecules vibrate more and more until eventually those long hydrocarbon molecules crack and turn into shorter hydrocarbon molecules. At this end I would have an inverted test tube filled with water, ready to collect any gases given out from this delivery tube. I'm going to use this model to show you what happens during cracking. So we've got a model of decane here with 10 carbon atoms, and during cracking, when the hydrocarbons are heated up and passed over the hot catalyst, they vibrate more and more until eventually at some point in the molecule it breaks into two or more different molecules. So what we've actually got is a shorter alkane molecule. This is octane, which is a very useful molecule because it's the main component of petrol. And we've also got this here, which has now not got enough hydrogen atoms. So it forms a double covalent bond. So we've actually also formed an alkene, in this case ethene. And they're very useful molecules because those alkenes can be joined together to make polymers. Here's an equation to show cracking. So if we start off with a long hydrocarbon like decane and heat it up until the molecule vibrates so much that it breaks, and it could snap down there, for example. One of the products we get is octane, which is a shorter hydrocarbon good as a fuel. Now take a look at this hydrogen atom. That one ends up there to complete the octane molecule. That means that we've now only got 4 hydrogen atoms in this molecule, and the carbon atoms still need to make 4 covalent bonds. So it makes this double bond, so we're now also making an alkene, in this case ethene. So cracking produces 2 products, a shorter alkane and also an alkene. The alkene molecules obtained from cracking crude oil can be joined together in a reaction called polymerization, and it takes high pressure to squeeze the molecules together and also a catalyst, and during those conditions what happens is the double bond starts to open up so that these small monomer molecules can join together to make a very long polymer molecule. In this case we're starting out with lots of small ethene molecules, so when we join them together to make a long molecule, it forms a molecule called polyethene, otherwise known as polythene. Polymers like polyethene would be made from thousands of monomer molecules joined together, so you'd end up with a really long molecule, so it would be impossible to draw the whole molecule. So when it comes to writing equations for these, we realise that all we need to draw is a section of the molecule and say it's repeated many times over. The small molecules we start with are called monomers, and when we join them together to make a long molecule, that's called a polymer. So let's imagine that we start off with 3 molecules of ethene and join them together. They would make a longer molecule of polyethene, and we can see the 6 carbon atoms represented in that long molecule. But really, instead of drawing it that way, we could say, well, we're starting off with 3 molecules of this, And the long molecule we get is really the same thing repeated 3 times over. And notice how I'm showing those double bonds sticking out. So if we start with 3 molecules of ethene, we would make a molecule like this, but it would be 3 times longer. But in practice, we might have 10,000 molecules of ethene. So what we do is we use N, which stands for a large number. So a large number of ethene molecules, when we join them together, it will make a long molecule that looks like this, but it will be many times longer. If we start with 10,000 of these, it would look like that 10,000 times over. And this is how we show a polymerization reaction. In your GCSE exam, the examiners will often give you the first half of a polymerization equation and ask you to complete it. So all you simply do is first of all open up that double bond. The rest of the molecule is the same, so we started with chloroethene with that chlorine atom there, and the rest are hydrogen atoms, just like with ethene. We put the brackets on, making sure the double bonds are poking out through the brackets, and the N comes down to there, to show we'd get a long molecule called polychloroethene, which would look like this many times over. If you still feel a bit unsure about any of the topics I've covered in this whole topic video, head over to my playlist C9 Organic Chemistry, where I've got a video on each of the different topics in a bit more depth with more examples. Also remember to check out my website, revisechemistry with mrb.co.uk. Thank you for watching.